calculus in high school, and we know it includes integration and differentiation. But what is it actually used for and how? The language of calculus appears everywhere in modern science and technology, whether we're modelling the rise and the fall of the stock market or determining exactly when a space rocket will arrive into Earth's orbit. It's the language invented for the specific purpose of describing the dynamic nature of our universe. To put it simply, calculus is the maths of motion and change. The word calculus originates from the Latin word meaning pebble. The Romans used pebbles to perform calculations on an abacus, and the word became associated generally with computation, just like the word calculator. The beauty of calculus is not just in the maths alone. It's in the way that calculus can form a connection, a relationship, and a language to describe the dynamic nature of our world. There are unlimited uses and benefits of calculus in any field. Calculus is the language of motion and change, and by using calculus, we have the ability to find the effects of changing conditions on a system like the weather, for example. In the atmosphere, we have changing temperature and changing pressure. So by using differential equations, meteorologists can indicate and predict the weather for our benefit. Calculus holds incredible power over the physical world by modelling and controlling systems. It's the language of medical experts, scientists, engineers, statisticians, physicists and economists. If a quantity or a system is changing, we can use the mathematical modelling of calculus to analyse the system, find an optimal solution and predict the future. Motion, electricity, heat and light, harmonics and acoustics, astronomy, radioactive decay, reaction rates, birth and death rates, costs and revenue, all of these can be modelled beautifully using calculus. In calculus we have two different branches. The first branch is differential calculus, and this involves the concept of the derivative of a function. This branch of calculus studies the behaviour and rate at which a quantity like distance, for example, changes over time. When we use the process of differentiation, we are essentially analysing the changing rate of a quantity and making predictions about its behaviour. Both these branches, differentiation and integration, are connected together by something called the fundamental theorem of calculus. This theorem, created by Newton and Leibniz, states that differentiation and integration are inverse operations or opposites. Just like yin and yang, black and white, or matter and antimatter can be used in aerospace to describe a rocket launch. If an object is in motion like a rocket, we can use calculus to model it. The thrust of a rocket into space is based on the calculus of motion, which physicists term momentum. In rocket physics, we are applying Newton's second and third law to a rocket that has a variable mass. How is the mass variable? The rocket's mass is decreasing over time as the fuel propellant is being burned off. As the rocket propellant ignites, the rocket experiences a very large acceleration as the exhaust exits out the back of the rocket at a very high velocity. This backwards acceleration exerts a push force on the rocket in the opposite direction, causing the rocket to accelerate upwards. The force acting on the rocket, called the thrust, is the rate of change of momentum, which is the first derivative of momentum. Using calculus, momentum, or the amount of motion of the rocket, p, equals mass times velocity. And so the rate of change of momentum, p' equals dmv dt, the thrust of the rocket. We can also write this as a physics equation, F equals ma, Newton's second law, and rewriting this from a calculus standpoint, F equals m times by the first derivative of momentum dv dt. To put it simply, the thrust of the rocket during a launch is the first derivative of momentum. A lot of people dream about running their own business. Wouldn't it be great if you could work out exactly how to maximise your business profits and help build a thriving company? Well, calculus can be used to maximise profits and revenue for any business. In actual fact, calculus provides the language of microeconomics and the means by which economists can model and solve financial problems. Of calculus can be applied in any scenario of change or motion, whether it be aerospace, economics, medicine and more. The benefits of calculus are endless, and if we have any problem in any dynamic situation that involves either change or motion, you can be sure that we can turn to calculus as a tool to model the problem and provide us with the answers.
When it comes to multivariable calculus. So the first thing we got to get straight is, what is this word multivariable that separates calculus as we know it from the new topic that you're about to study? Well, I could say it's all about multivariable functions. That doesn't really answer anything, because what's a multivariable function? And basically, the kinds of functions that we're used to dealing with in the old world, in the ordinary calculus world, will have a single input, some kind of number as their input, and then it outputs just a single number. And you would call this a single variable function, basically because that guy there is the single variable. So then a multivariable function is something that handles multiple variables. So, it's common to write it as like x, y. It doesn't really matter what letters to use. And it could be, x, y, z, x1, x2, x3, a whole bunch of things. But just to get started, we often think just two variables. And this will output something that depends on both of those. Commonly it'll output just a number. So you might imagine a number that depends on x and y in some way, like x squared plus y. But it could also output a vector, right? So you could also imagine something that's got multivariable input, f of x, y, and it outputs something that also has multiple variables. Like, I'm just making stuff up here, 3x and, 2y. And this isn't set in stone, but the convention is to usually think if there's multiple numbers that go into the output, think of it as a vector. If there's multiple numbers that go into the input, just kind of write them more sideways like this and think of them as a point in space. Because, when you look at something like this, and you've got an x and you've got a y, you could think about those as two separate numbers. Here's your number line with the point x on it somewhere. Maybe that's 5, maybe that's 3, it doesn't really matter. And then you've got another number line, and it's y. And you could think of them as separate entities. But it would probably be more accurate to call it multidimensional calculus, because really, instead of thinking of, x and y as separate entities, whenever you see two things like that, you're going to be thinking about the xy plane and thinking about just a single point. And you'd think of this as a function that takes a point to a number, or a point to a vector. And a lot of people, when they start teaching multivariable calculus, they just jump into the calculus. And there's lots of fun things, partial derivatives, gradients, good stuff that you'll learn. But I think first of all, I want to spend a couple videos just talking about the different ways we visualize the different types of multivariable functions. So as a sneak peek, I'm just going to go through a couple of them really quickly right now, just so you kind of whet your appetite and see what I'm getting at. But the next few videos are going to go through them in much, much more detail. So first of all, graphs. When you have multivariable functions, graphs become three-dimensional. But these only really apply to functions that have some kind of two-dimensional input, which you might think about as living on this xy plane, and a single number as their output. And the height of the graph is going to correspond with that output. Like I said, you'll be able to learn much more about that in the dedicated video on it. But these functions also can be visualized just in 2 dimensions, flattening things out, where we visualize the entire input space and associate a color with each point. So this is the kind of thing where you'd have some function that's got a 2-dimensional input. It would be f of x, y. And what we're looking at is the xy plane, all of the input space. And this outputs just some number. Maybe it's like x squared. This particular one is an x squared, but that and maybe some complicated thing. And the color tells you roughly the size of that output. And the lines here, called contour lines, tell you which inputs all share a constant output value. And again, I'll go into much more detail there. These are really nice, much more convenient than 3-dimensional graphs to just sketch out. Moving right along, I'm also going to talk about surfaces in 3-dimensional space. They look like graphs, but they actually deal with a much different animal that you could think of it as mapping 2 dimensions. And I like to sort of push it about. And we've got kind of a 2-dimensional input that somehow moves into 3 dimensions. And you're just looking at what the output of that looks like, not really caring about how it gets there. These are called parametric